Alright, this is chapter 4, number 34. It's a pretty classic Atwood machine type of problem where you got two masses attached over top of a pulley. My picture here that I've drawn is, again, straight out of your book. So the question reads, the two masses shown in the figure each are initially 1.8 meters above the ground, and the massless, frictionless pulley is 4.8 meters above the ground. What is the maximum height, what maximum height does the lighter object reach after the system is released? And then it says, for a hint, first determine the acceleration of the lighter mass and then its velocity at the moment the heavier one hits the ground. This is its launch speed. Assume that it doesn't actually hit the pulley. Okay, so you got to make a few assumptions in here, but it's pretty clearly stated in the hints. Okay, so the one thing that we should recognize right off the bat, that is, if they are different masses, then their weights are different. Okay, so then I know that the sum of their forces, okay, is going to be the difference between 31.4 and 21.6. And if that's the case, then that's 9.8 newtons. That's the sum. Okay, so I also know that the sum of the forces is equal to ma. So then 9.8 equals the mass. Now it's got to be the total mass of the system. So 2.2 and 3.2 is 5.4 times a, and divide by 5.4 on both sides, and we're left with a equals 1.81 meters per second squared. Okay, so that's part of the problem. Okay, the real problem is, what is the maximum height, or what maximum height does that lighter object reach? Now keep in mind, because this one's heavier, this one's going to go down and this one's going to accelerate up. So there's going to be an acceleration on this particular object upwards. Okay, one thing that we're going to try to figure out is, okay, well, if they're attached by a string, if this one falls at this acceleration and this one rises at that acceleration, then the velocity of either one when this hits the ground is going to be the same. Okay, so I'm going to use some kinematics to figure this out. I want the final velocity. We know that the initial velocity of each object is 0. And I have an acceleration now, and I know that this object has got to fall 1.8 meters. Sorry, I kind of had that a little off screen there. So that's all the information I need. Okay, so v squared, this is 0, so that goes away. 2 times 1.81 times 1.8 meters. And if we do that, don't forget to take the square root to get rid of all that stuff, and you end up with a velocity of 2.55 meters per second. Okay, now I just want you to keep in mind that this object was originally 1.8 meters above the ground. Okay, by the time this one hits the ground, this one's going to move another 1.8 meters up. And that's where this velocity is going to be. This velocity is going to be at 3.6 meters. That's how high that's going to be up in the air. Okay, so once I know that this is the final velocity after this box hits the ground, okay, this velocity will now become the initial velocity of this box when it's at this point. So I can again use the same equation, v squared, v naught squared, plus 2a delta x. Now, I now know that this initial velocity is 2.55. Okay. What is the final velocity of any object at its maximum height? What's that? Oh, it's 0. Yeah, that's what I thought. Okay, good. Okay, plus 2, and then once the other one hits the ground, what causes the object to slow down to this particular velocity? It's gravity. All right, so we got negative 9.8. And delta x is going to tell us how high above this point, this release point, the object gets. So we got to go ahead and solve this problem, and if you do it, and I'm not going to show you the math steps, you get 0.33 meters. Okay, so now the total height that this object reaches is 1.8, that's how high it was to begin with, plus another 1.8 while this object falls to the ground, plus 0.33. So you end up with 3.93 meters high. Okay, so that's a three-part problem, but definitely doable. All right.